We've talked about much of what will be used when applying the mole concept. Now, there's a common approach that we can take when we're answering questions about the mole concept. You first find the number of moles, then use mole ratios to convert those number of moles into the number of moles for another substance. And then after you convert the number of moles, you use that number of moles to calculate for the needed quantity. You will get even more understanding of this approach when we get to answering the questions. We're going to have 3 examples to make you able to understand how we can apply the mole concept. In our first example, we're being told that phosphine pH 3, which is a gas and has a smell of garlic, is formed when phosphorus is warmed with aqueous sodium hydroxide. The equation here below is showing that reaction that leads into the formation of phosphine and sodium hypophosphite. We're asked to calculate the maximum mass of phosphine formed when 7.4 grams of phosphorus reacts with excess aqueous sodium hydroxide. Later I'll explain as we are solving why they tell us this phosphorus is being reacted with excess aqueous sodium hydroxide. If you can remember the approach I was just talking about, you can realize that the first thing we need to try to do is to find the number of moles. So whenever you have a question, try to look at the information you've been given. Which of these substances that is in this chemical equation can I find the number of moles the easiest? As you can see, we have the most information about phosphorus, 7.44 grams of phosphorus. Okay, now we know that this is mass, therefore we're going to use this equation to find the number of moles. The molar mass of phosphorus is 31, as you can see. So N will be equal to 7.44 divided by 31. Now we're going to do that on a calculator. As you can see, we have a 0.24, meaning N is equal to 0.24 moles. So what this indicates is that in 7.44 grams of phosphorus, we have 0.24 moles. If you don't understand that, please check the video about how to use mole concept formulas. Now, we have the number of moles. The next step was us using mole ratios. How are we going to use our mole ratios? Remember that from the examples we looked at when we were looking at the concept of mole ratios, we were able to find the number of moles of something we didn't have using something we had. So here it's like they're telling us 0.24 moles of phosphorus are reacted with excess aqueous sodium hydroxide. How many moles of phosphine are produced? That's the question you ask yourself on the second step. That's very simple. We have this ratio of phosphorus to phosphine that is standard 4:1. It's simplified. We can simplify this further, and then we get a ratio of this 0.24 to the X that we don't know, because we know that the proportion in which phosphorus will make phosphine won't change. So if we have a 0.24 to X and we cross multiply, we will be able to find the value of X. 4 times X is going to give us 4X, and 0.24 multiplied by 1 won't change anything. So we have a 0.24 again. Therefore, what we're going to do here is get rid of this 4 by division. We cancel it on our left side because we have something multiplied and something divided that is the same, meaning it's playing no role. Again, we get our calculator and find the value of X. You can see our answer is 0.06. Therefore, X is equal to 0.06 moles. And remember, these moles we've just found are for phosphine. Now, since we've done step 1 and step 2, the thing left now is finding the needed quantity. We found the number of moles of phosphine, but that's not what was asked. We were asked to calculate the maximum mass of phosphine formed. And so we come back and check our formulas. Which of the formulas can be used to find the mass? Of course, it will be N is equal to M over MR, but we need to make M the subject of the formula. M will be equal to N multiplied by the molar mass. So we're going to get N, which we're just from finding, 0.06, and multiply it by the molar mass of phosphine. Now, Not that we don't have the substance phosphine on the periodic table, but we have the individual elements that make phosphine on the periodic table. What I mean is that we have the atomic mass of phosphorus, and we can find the mass of 3 hydrogens that are found in phosphine. Therefore, it's just like we did in the video about how to use more concept formulas. We're going to find the molar mass of phosphine. Phosphorus is 31, but before we do that, let's get to know how many atoms of phosphorus are in phosphine. You can see that it's 1. For hydrogen, we have 3. Now we multiply these numbers that we have by the atomic masses of their respective elements. So phosphorus will be 31, as you can see. Hydrogen will be 1. And then we just add the products. Here we have 31, here we have a 3. You can see that our answer will be 34 after we have found the molar mass. What you notice is that I'm just using one line to underline my answers, because I don't want to get confused and get comfortable that I've found the final answer. The final answer is what will be underlined with 2 lines. Okay, our answer is 2.04, meaning that's the maximum mass of phosphine that can be formed when 7.44 grams of phosphorus reacts with excess aqueous sodium hydroxide. Now, the reason why they tell us this reaction had excess aqueous sodium hydroxide is to make us know that none of the phosphorus in this 7.44 grams didn't get reacted. Now, let's look at a second example. In this example, we have aqueous ammonium nitrate with this formula here, which decomposes when heated as shown below here in this chemical equation. In this question, we've been told that a 250 cubic centimeter sample of 0.150 mole per cubic decimeter of ammonium nitrate is heated. Don't get confused about this information. I'll tell you how we are going to know how to use it. Then we're asked to calculate the maximum volume in cubic decimeters of nitrogen, this here, which is formed at room temperature and pressure. They've told us quite a lot here, and if you don't take the information in bits, you might get confused. The first thing is you looking at this 0.150 mole per cubic decimeter. What is this telling us? If you can remember, this mole per cubic decimeter is the unit for molar concentration. So they've given us the concentration of this ammonium nitrite, and they've also given us the volume, meaning if we use this formula, we can find the number of moles. Remember, we still have the first step as finding the number of moles. So N will be equal to C multiplied by V. Our C is 0.15, and then our V is this 250 cubic centimeters. Now, remember that it was indicated that volume when we are finding concentration should always be in cubic decimeters or should always be in liters. After converting this 250 cubic centimeters into cubic decimeters, we're going to have a 0.25. What you do is just get this 250 and divide it by 1000. As you can see, we have 0.25. Now our job is to find N. 0.15 multiplied by 0.25. Our answer is 0.0375. So what this indicates is that in these 250 cubic centimeters of 0.15 mole per cubic decimeter of ammonium nitrite, we have this amount of moles. If you can remember again, what we're going to do is use more ratios. So this 0.037 will become very useful. But before we do that, let's get the standard mole ratios from the chemical equation. We have a 1-to-1 mole ratio, as you can see, meaning nothing will change. I'm just going to do that for showing you that nothing changes exactly. So we have that 1 and x being multiplied, and the 1 and 0.375. As you can see, x will be equal to 0.0375, because if we divide by 1, nothing changes still, and x remains 0.0375 moles. Now, after we have these moles of nitrogen, now let's find the maximum volume. Nitrogen is a gas. You can see that even from the state symbol. So we're going to be using this formula. We're going to make V the subject of the formula and find the maximum volume of nitrogen that can be produced. N is 0.0375 molar volume. Where we're going to get that from? Remember that molar volume has got two values, one for RTP and one for STP. So let's check in this question. Is there anything that tells us this was done in a lab? Of course, no. But you can see they've told us here at room temperature and pressure. So we're going to use 24. I still have my answer there. So I'm just going to hit multiplication. My calculator knows I want to multiply this answer with the 24. And I have my answer. You can do it separately. You see your answer will be still the same. Nitrogen produced will be 0.9 cubic decimeters. If this is converted to liters, this will be just 0.9 liters, which is about 900 mils. Now let's look at the last example, which consolidates everything we've looked at about the application of the mole concept. Here we've got an aqueous solution of calcium hydroxide, which was titrated with 1.5 molar hydrochloric acid. When we look at the topic acids, bases, and salts, you know what titration is. This is the reaction by which the calcium hydroxide gets titrated with the 1.5 molar of hydrochloric acid. As you can see, it's a simple reaction. So it required 60 cubic centimeters of the aqueous hydrochloric acid to neutralize 200 cubic centimeters of calcium hydroxide. Very important. Now we're asked to calculate the concentration in mole per cubic decimeters of the calcium hydroxide. Right from the start, this question might also look difficult, but it only becomes difficult if you don't know that molar or molarity is the same as mole per cubic decimeter. So this 1.5 molar is just the same as 1.5 mole per cubic decimeters. Now, since we know that, now we're going to look at which of these two will be the easiest to find the number of moles, because we know that the first step usually when we're applying the mole concept is finding the number of moles. As you can see, we've got the concentration of hydrochloric acid and we also have its volume, meaning it will be the easiest to find the number of moles for. So C is equal to N over V is the formula we'll be using, but we'll make N the subject of the formula. The concentration is 1.5. Again, you can see our volume is not given in cubic decimeters, so we need to convert this in cubic decimeters. We will do that by simply dividing this 60 by 1000, and we're going to have 0.06. You can do that on your calculator. I'm sure you've done that and you've proven that truly this 60 when divided by 1000 will be 0.06. .09 is the number of moles we have. These are the moles for hydrochloric acid. So now we need to create a mole ratio between hydrochloric acid and the calcium hydroxide whose concentration we want to later find. We use the standard mole ratios that are found in the chemical equation. HCl to calcium hydroxide is 2 to 1. Make sure you have it right. If you make the mole ratio 1 to 2, meaning you need to swap these. But like I said, we want to make mole ratios with the known one first and then the unknown one second. Now we have 0.09. If we keep the same proportion of 2 to 1, we can say that 0.9 will give us X. And therefore, as you can see, HCl is on our left, calcium hydroxide is on our right. We cross multiply, then we have 2X is equal to, here the one doesn't change anything, so it's 0.09. We divide by 2 on both sides to get rid of the 2 on our left. It cancels, and X is equal to 0.09 divided by 2. .045 is our number of moles of calcium hydroxide. So X will be equal to 0.045 moles of calcium hydroxide. Now we have the number of moles. We shouldn't get comfortable. As you can see, still I haven't underlined this answer with 2 lines. Now we need to find the concentration. How can we find the concentration when we have the number of moles of calcium hydroxide and we have the volume? Well, we'll use this formula. C is equal to N over V. the number of moles, which is 0.045. Obviously, we've had a lot of volume conversion here. You know that 200 will be divided by the 1000, and we're going to have 0.2. 0.045 divided by 0.2. Okay, this is our concentration, 0.225. C is equal to 0.225 mole per cubic decimeter. So this is the concentration of the calcium hydroxide solution that was used. As you can see in these three examples, we've made use of all the three formulas, meaning you should be able to work with any question. You have finally reached the bonus tip section. In today's bonus tip section, we have one tip for you, which is how to identify the formula to use. We can do this in a two-step process. The first step is you grouping your formulas. Once you group your formulas in the right way, which I'll show you in a minute, you will be able to identify the formula to use very easily. The first is you grouping this formula as a mass formula, because if you really look at this formula, we have mass on top and molar mass here. So think of this formula as a mass formula. Then we have a volume formula. In this formula, we only have volume, the volume of a gas divided by the molar volume. In the third, we have the concentration formula. You might argue to say, well, we have volume even here. Why don't we call it a volume formula? Well, I won't tell you to think of this one as a volume formula because it has concentration. And concentration, as you can see, is not found in these other two formulas. N is found in all of them. V is found in this one and this one, but this is the only formula that has volumes only. This is the only formula that has mass only, and this is the only formula that has concentration. So once you know how to group your formulas like this, mass, volume, and concentration, it will be easy for you to identify the formula when you become able to check the quantities that you've been given. The beauty about grouping your formulas is this. When you see mass as a quantity that you're finding or that you've been given, you know that you'll be working with the mass formula. When you've been given volume in a question, particularly volume of a gas, you need to use the volume formula. While if you've been given concentration like we did in question 3, as you saw, we mostly use the concentration formula. Thanks for watching this video till the end. It's your job now to go out there, get some questions and practice application of the mole concept. Watch out for that other video that will be covering more about stoichiometry.